All right, guys, welcome back. Today, we're kicking off a pretty massive series, a deep dive into the guts of back-end engineering and distributed systems. So if you're a back-end dev, you're in exactly the right place. We're going to be using Roberto Vitillo's amazing book, Understanding Distributed Systems, as our roadmap to break down all the concepts you absolutely have to know. Let's get right into it. We have to start with this quote from the legend himself, Leslie Lamport. It's kind of funny, a little bit terrifying, and it just perfectly nails the beautiful chaos we're about to jump into. And that's the world we live in, right? Our apps are tied into this huge web of services, and a failure way over there can ripple out and break things right here. Look, let's be real. Building a simple app on one server, that's the easy part. You can throw your code, your web server, your database, all of it onto one machine and call it a day. But what happens when you actually succeed? What happens when 1 million users suddenly show up? Well, that one server is going to fall over. Hard. I guarantee it. And that is the problem that forces us into this whole new world of distributed thinking. So what even is a distributed system when we get down to it? Well, at its core, it's just a group of nodes that work together by passing messages back and forth over a network to get something done. And when I say node, don't just think of a big server rack. It could be your phone, a process running on your laptop, anything. The trick is making all these separate pieces work together so well that they look and feel like one single solid application. So why do we even do this to ourselves? Why deal with all this complexity? Well, a lot of the time we just don't have a choice. Some things, like the internet itself, are just distributed by their very nature. For others, like Dropbox, you need to copy your files across tons of machines for high availability. So if one server blows up, your photos are still safe. And then there are jobs like Google trying to index the entire web that are just way too big for any single computer on Earth to handle. Okay, so to make any of this stuff work, we have to solve 5 really big fundamental challenges. We're going to walk through every single one, and we'll start with the most basic one of all. How do these nodes actually talk to each other? Communication is so much more than just sending a message. First, you have to figure out how to represent the data. Is it JSON? Is it protobuf? Then, you've got to deal with the network itself, which is just inherently unreliable. Packets get dropped, bits get flipped, somebody might cut a fiber optic cable with a backhoe. It happens. And on top of all that, you have to lock it down so nobody's snooping. Now, we use libraries to hide a lot of this mess, but you have to remember, abstractions leak. And you absolutely need to know what's going on underneath when things eventually break. All right, so our nodes can talk to each other. Now for the really hard part. How do we get them to agree on things and actually work together? This is the challenge of coordination, and honestly, it's where some of the wildest problems in computer science live. And this whole challenge is captured perfectly in this famous thought experiment called the two generals problem. So imagine you have 2 armies, and they need to coordinate a simultaneous attack. The only way they can communicate is by sending a messenger through enemy territory. And that messenger, well, they might get captured. So let's just walk through this. General number 1 sends a messenger. Hey, we attack at dawn. Okay, cool. General 2 gets the message and sends a confirmation back. Got it, attack at dawn. But now, General 2 starts to sweat. Did my confirmation actually make it? Because if it didn't, General 1 won't attack and my army will get wiped out all by itself. So General 1 would have to send a confirmation of the confirmation, and you can see how this becomes an infinite loop. Here's the kicker. It is provably impossible for both generals to ever be 100% certain. And that is the absolute core of trying to get consensus over a network that you just can't trust. Okay, let's move on to our third big challenge. Your system's up, it's running, nodes can talk and coordinate, but now how does it handle more and more work? This is the whole game of scalability. We pretty much measure scalability in 2 ways. First, there's throughput. That's just how many requests can you chew through per second. And second, there's response time, or latency. That's how long a user has to sit there staring at a loading spinner. A system that scales well can handle a ton more load without making users wait any longer. So, when you eventually hit your limit, and you will, you've got 2 basic choices. The old school way was scaling up, or vertical scaling. You just buy a bigger, faster, more expensive server. But there's a limit to how big a server you can buy. The modern way is scaling out, or horizontal scaling. Here, you just add more cheap, regular machines and spread the work across them. And in the world of the cloud, this is the name of the game. Which brings us to challenge number 4. When you have hundreds or even thousands of machines all working together, one thing is an absolute guarantee. Something is always broken. Resiliency is all about designing your system to not just survive, but to thrive in this constant state of partial failure. We talk about this with the nines of availability, and the difference in the real world is just huge. 3 nines or 99.9% uptime sounds pretty good, right? But that's still almost a minute and a half of downtime every single day. 4 nines, 99.99%, gets that all the way down to just over 8 seconds a day. That's a massive difference in user experience, and it's something you have to design for from the very beginning. This all leads to probably the biggest mental shift you have to make. You have to accept it. Hardware will die, networks will get flaky, deployments will have bugs. Your job isn't to somehow prevent every possible failure. That's impossible. Your job is to design a system that expects failure and can handle it so gracefully that the user doesn't even notice. And that brings us to our fifth and final challenge, the one that's so easy to forget about when you're just starting. How do you build these incredibly complex systems so that we, the humans, can actually operate them, debug them, and add new stuff to them over time? That is maintainability. You know, most of the money spent on a piece of software isn't in building it the first time. It's in everything that comes after. Fixing bugs, operating it, adding features. That's why having a rock-solid testing strategy, unit, integration, the whole shebang is just not optional. And on the operations side, you've got to have great monitoring to see what the heck is going on, and tools like feature flags so you can roll out changes safely. Okay, we just covered 5 huge high-level challenges. So how do we actually start building something while keeping all that in mind? Let's bring this down from 30,000 feet and look at the anatomy of a single service. A really powerful pattern for this is called ports and adapters. Right in the middle, you have your core business logic. This is the good stuff, the thing your service actually does, and it's totally protected from the outside world. To get requests into that core, you use what's called an inbound adapter, like an HTTP endpoint. And for your logic to talk to something else, like a database, it goes through an outbound adapter. The beauty of separating things this way is that you can swap out your database or your API tech without ever having to touch that precious core logic. So, that was a whirlwind tour through the absolute foundations. If you only take one thing away from all of this, let it be this. Building distributed systems isn't just about new tools. It requires a completely new way of thinking about software. And that really brings us to the central question we're going to be chipping away at in this whole series. It's the great paradox of what we do. If we know for a fact that individual computers will fail, that networks are unreliable, that perfect coordination is impossible, then how on earth do we glue all these unreliable parts together to build systems that, to our users, feel completely and totally reliable? That's the magic we're trying to create. And in the next part, we're going to start by diving deep into the communication layer. You are not going to want to miss it.